Hello, welcome back to a new lesson on the harmonic oscillator. In this video I'm going to introduce a very important concept in mechanics, the phase space. We're used to representing variables one versus the other, position versus time, force versus time, potential energy versus position. But in a dynamical system such as the harmonic oscillator, we can choose as variables to plot the position and the velocity. These two variables give us the information about the particle at one instant in time. For motion in one dimension, we have two axes, x and x dot. For a three-dimensional motion, this would lead to six-dimensional space. 3 axes for the position and 3 for the velocity. If we have two particles, this would need 12 axes, and for an n-particle system would need a 6 n-dimensional space. The system, at a given time, is defined with one single dot. There is no explicit dependence with time in phase space, but we can draw the evolution of the system in it. Let's consider the simple harmonic oscillator. Let me write the equation for the position and for the velocity. We can square both expressions and solve for time. Then we can eliminate time and get the equation of the trajectory in phase space. Be aware that this is not the trajectory in real space, but in phase space. This equation is the equation of an ellipse. Now let me rewrite these denominators using the energy of the simple harmonic oscillator. So we see that these ellipses are such that the semi-axes that define it depend on the energy of the system. So each one of these ellipses corresponds to a different energy of the oscillator. The system moves along these ellipses with constant energy. These curves will not cross, as that would give a crossing point without a well-defined energy. The system is conservative. It can only go from one ellipse to the other by gaining or losing energy. Let's look at one of these ellipses. Consider we are in one specific point of one of them. This one, for example, has positive position and positive velocity. Because of the positive velocity, the system is moving in the direction that increases x. That is moving to the right. We see that the velocity is going to decrease. At some point it will cross zero, which happens when the oscillator is at its maximum position. Then, continuing with the ellipse, the system changes to have negative velocity, so it moves to decrease x. At some point it will have minimum velocity, which happens at the origin, and so on. We can follow the motion by just looking at the trajectory in phase space. The oscillator moves in a clockwise direction in phase space. Fantastic! Yeah, you're right. Then, what happens for the damped harmonic oscillator? Let me write the equations for the position and velocity for the underdamped harmonic oscillator. Yes, you're right, we can't follow the same steps as before. We can't solve this for time to find the equation of the trajectory in phase space. What I'm going to do here is to use my computer to plot position versus velocity. I define a range of time values, I substitute in x of t and generate values for the position for each time. Then I do the same for the velocity. And finally, I plot v versus x. This is a spiral, and it makes sense, doesn't it? So the system is losing energy to the environment. That's why its velocity is being reduced. The oscillations are getting smaller and smaller. The amplitude is being reduced. Remember that the exponential term in equation for the position, that term makes the amplitude to decrease exponentially. So the radius of the trajectory in phase space decreases also. What about the overdamped harmonic oscillator? Well, the same. We need a computer for that and follow as before. For the damped and driven harmonic oscillator, the situation is much simpler. If we focus in the periodic motion after the chaotic transient, that's just a simple harmonic oscillator again. Phase space is a very helpful tool when we want to study a dynamical system for which we don't have analytical solutions, but we still want to understand its motion. We'll be seeing more of this in coming lessons. May the science be with you.